All right, so welcome to today's math class, everyone. Today we'll continue our journey through integration. Specifically, we'll talk about two important integration techniques, integration by parts and integration by substitution. Before we do that, however, a brief warm-up, so you get a chance to think about what we covered yesterday once again. So here's two old exam problems. The first one should be very quick. The second one shouldn't be that long either. So take a few minutes to think about those and see what solutions you get. And for those of you who are done already, there's two tweetback quizzes online asking for your assessment of how hard you found those problems. So once you're done, please vote for that so that I have an indication of how many of you are done already. It's been about 9 minutes. Quick show of hands. How many of you are done? Who needs more time? So let's add 1 minute. All right, let's take a quick look. Here's your assessment of the first problem. Interestingly, that is a rather mixed feedback. So some of you seem to think this is hard, many seem to think this is easy, or somewhere in the middle. I'd say the hard part of this is probably, if there is any hard part to this, the hard part is probably guessing the right expectations, not making it too complicated. So very quickly, let's write down the solution to that one. That was 2019-211. So you have this function here, basically a piecewise defined function, 4 different intervals, and I'm asking for the total volume of sales. So this is the sales at any given point in time. I'm asking for the total volume of sales between 8 and 1700. Devise a function to compute that value. And the question just asks you to write down a suitable expression, no computations necessary. Basically, what I want to see is you understand what this means and you understand how to use this to compute a total volume. So basically, we need to sum up over all the sales that happened between 8 o'clock and 5 o'clock. This is a continuous function, so we can't just sum it up. It's no discrete points in time. So what we would do, of course, is we would compute the integral over that function from 8 o'clock to 5 o'clock. Right, so that is what you need to do here. You compute the integral from 8 to 17 of s of t dt. And then all you have to realize is, well, this is a function that's defined piecewisely, so I have to split that up to actually use these expressions here. We're starting at 8 right here. So that first part is completely irrelevant. We start with that one. So the first integral starts at 8, integrates over t squared minus 16t plus 68 dt. This part is valid until 11 o'clock, so we integrate that from 8 to 11. Then for the next part, this one starts here at 11 and is valid until 4 o'clock in the afternoon. This is the expression, so that's the next part of our integral. So we add the integral from 11 to 16 over minus 1 over 5 t minus 11 plus 13 dt. And we're not quite at 5 o'clock yet, so we need to add a little more of that last part here that starts at 4 o'clock and goes to midnight. And of course, we don't integrate until midnight. We only integrate from 4 o'clock to 5 o'clock, 16 to 17. And now the expression is the last one here, 2t minus 16 squared plus 12 dt. Right, so that was the answer that was expected in this exam. Okay, and please make sure to carefully read the problem statement. It explicitly says you do not need to actually compute the correct value. So stop at this point, don't start evaluating those integrals. Of course, that's not hard, but it will cost time. All right. So that's this first problem here. For the second one, this is your assessment, and most of you found that very easy, apparently. And that, of course, was the intention. So for 2016, one number 10, that's asking for an antiderivative of this polynomial. So basically, you have to integrate this polynomial with an additional property, this here. So let's start by integrating this polynomial first, the integral, integral of f of x dx. We need the indefinite integral here. F of x is 3x squared minus 2x plus 1 dx. So what we get is, well, x squared integrated is x to the third over 3 times 3, that's x to the third, minus 2x. If I integrate x, I get x squared over 2, so times 2, that's minus x squared, plus 1, integrated is plus x. And then, of course, add a constant. So that's the class of all possible antiderivatives. And now I just want to filter out the one with that property here, f of 0 equals f of 0. So first thing I have to do is compute this value. Right, f of 0 is, well, that's 1, obviously, right? 3 times 0 minus 2 times 0 plus 1. So what I need to satisfy is capital F of 0, which is c, needs to be equal to 1. And then I get, well, the constant is 1, obviously, so here's my correct capital F, x to the third minus x squared plus x plus 1. And that's it. And again, please make sure to carefully read the problem statement. Notice it says capital F of 0 is f of 0. It doesn't say capital F of 0 is 0. And many people misread that. Right? So I guess, my guess would be this, there's nothing complex or complicated or challenging about these problems. They should be fairly quick as long as you carefully read the problem statements. Any questions about those? Good. So then let's go on. By the way, that first problem here, the sales function, that hopefully reminds you of this part of the video. So I'm going to skip over that right now. Progressive income tax, basically the same thing, right? Again, you have an example of a function that's piecewisely defined, and you integrate over a specific part of that function. Same idea. All right, so let's start with integration techniques. We're going to learn about 2 integration techniques today that are often very handy. The first one is probably the easier one, integration by parts. Basically, the idea of that is to transfer the product rule of differentiation into the integration world. So remember that here is the product rule of differentiation. If you want to compute the derivative of a product of 2 functions, you first compute the derivative of f times g, and then f times the derivative of g. If you integrate that whole expression, you get this result here. Right? So f times g is the integral of f prime g plus the integral of f g prime. And basically that is the integration by parts rule. It's usually reformulated so that it starts with this expression here, but that's all. Okay, so here's the theorem, integration by parts. We have 2 functions defined on an open interval as usually. Both need to be continuously differentiable on that interval so that we can use those derivatives here. And then this integral of that form, f prime times g, can be reformulated to this expression, f times g minus the integral over f times g prime. Yeah, so basically you take one of these functions, this one here, you integrate that. So you start with f prime here, and here you have f instead of f prime. And you have one function g, and you differentiate that in the integral. And of course, that will help if this expression here becomes easier, usually. So that means by differentiating g, you should win something. The function should become easier. And of course, you can only do that if integrating this part is not too hard on its own. Right? So the question is this expression in the integral, can I decompose that into two parts? One that is easily integrated, that's going to be my f prime. And one that becomes a whole lot easier if I differentiate that, that's going to be my g. Okay, and of course you can also use that for definite integrals, same thing. Here's a quick example. For example, you can use that trick to integrate the ln function. If you want to do that, it's not immediately obvious how to do that. You have to reformulate that into a product, but of course you can do that by just rewriting that as 1 times the ln function. And ln is a function that might not be easy to integrate. We don't know the integral yet, but it's easy to differentiate. And if I differentiate the ln function, what I get is 1 over x, so that seems a lot easier. Okay, so the hope is that differentiating that, we'll obtain an easier expression, and integrating 1 is not hard, that's just x. Well, that's exactly what we do. So using this integration by parts rule, we say, well, this is f times g, so x times the ln, minus, and now the roles are reversed, so instead of f prime g, you write f g prime, so that's x times 1 over x. Well, now obviously x over x is just 1, so that has indeed become a whole lot easier. And we can just compute that integral right away. So this here is the result, x ln x minus x. Of course, for the indefinite integral, we add a constant. Okay, so by using this nifty little trick, it's easy to compute the integral over the ln function. One other example that demonstrates another use case of that integration by parts is this one here. So you want to integrate over that function sine cosine. It's not immediately clear that this will help anything. I mean, it's easy to integrate the sine, it's also easy to integrate the cosine, but taking the derivative doesn't really change a lot, right? So taking the derivative of the sine yields the cosine. For the cosine, it yields the negative sine. So that doesn't seem to make things a whole lot easier. Still, if you just give that a try, what you get is first this expression, f times g, that's simply cosine squared. And then if you apply that, rule here, what you get here is the negative cosine. And if you differentiate the cosine, you get the negative sine. So what happens is, basically, the roles of these two are reversed. So you end up with pretty much the same integral as what you started with, but now you've added this term here. And the nice thing is, there's a minus in front of this now. So that means you can just take this to the left. Right? If you do this, you get this integral 2 times on the left equals minus cosine squared. And suddenly you have an equation that you can solve for the integral. And if you do that, this is the result that you get. So using this trick, you were actually able to solve that integral without explicitly integrating something, basically. Okay, that's also, that might help with this integration by parts rule, if somehow you get the integral to show up again, to rise out of the ashes in a way. The only thing you need to make sure is that the sign is right. So if you get plus, here in the end of minus, then of course you didn't win anything, or not a lot, because taking it to the left would just cancel out the integral, and you don't want that. Yeah, but it's usually worth a try. So if you have sine, cosine functions, things like that might be worth a try to see if you get the integral to rise again. All right, so 2 typical use cases of integration by parts. Maybe let's start with an example before we go on. We do have the homework here that would provide us an example. So take a look at 14.2. We'll start with B. That says use integration by parts to determine this integral sine x squared. So let's take a look at how we can do that. We want to integrate sine x squared dx. And just as a quick remark, I'm not sure if I discussed that already. So there's a nice shorthand for this sine x squared notation that might also be confusing. So I just like to mention that briefly. People often abbreviate that as sine squared x. That means the same thing. It's not the most precise notation, unfortunately, but it still saves some time in writing. So if you want to use that, you're welcome to do that. I'll try to avoid that because it seems to be confusing for some people. Just to mention that. Okay. Now, let's see. If we want to solve this integral here, first we need a product of 2 functions. And it should be pretty obvious how to get that here. Well, sine of x squared is the same as sine of x times sine of x. Right, so here we have 2 functions. And let's just say this first is f prime and this is g, doesn't really matter. And let's try using integration by parts. Well, if we do that, we need to integrate that sine function. The integral of the sine is the negative cosine. So that's minus cosine x times sine x. And then we subtract the integral of, well, we integrate this part here. Again, that's minus cosine x. Times, and then we differentiate the sine, and that simply yields the cosine. Okay, so at this point, it doesn't seem very useful yet, but let's go on just a little bit. So here we have minus sine times cosine, just rearrange that. Here we get plus, right? This minus and this minus, I can just take that out. It's a plus. The integral, and I have cosine 2 times, so that's cosine of x squared. And of course, what I'd like to have is, well, not this integral, but rather this integral, so that I get this reproduction effect. Well, how can I obtain that? Actually, again, an easy reformulation. What I'm using now is the fact that sine of x squared plus cosine of x squared is 1. And some of you have asked what facts you need to know about the sine and the cosine for the exam. This is one of the facts you absolutely need to know. So those sum up to 1. And that means I can get back my sine squared integral if I just replace this cosine by 1 minus sine squared. So that's what I'm going to do. So this is 1 minus sine of x squared dx. Well, and here we are. Minus sine x times cosine x. There's a plus on here, sorry. Plus, well, let's split up the integral. Integration over 1, that just yields x, so I can do that right away. Minus, and then I get minus the integral over sine x squared dx. And now you can see this integral here is the same as this. So now I have an equation I can solve for the integral. And that's what I'm doing. So that means this integral over sine x squared dx, or 2 times the integral actually, is equal to, let's start with the x, just to not start with the minus, x minus sine x cosine x. And of course, if I just want to have the integral here, I need to divide that whole thing by 2. So here's the result. And just to mention that, of course, there is a number of other ways to get that same result here, yeah, especially with trigonometric expressions. There's a bunch of theorems, trig theorems that you can play around with if you want to. I just don't like those very much. All right, any questions about that? Then maybe let's go on. Let me quick look at tweetback. Nothing I need to answer right away. Okay, so let's go on with the next integration technique before we do more examples. The next one is called integration by substitution. And again, this goes back to taking one of the rules of differentiation and transferring it to the integration world. We have product rule before. Now this time we are looking at chain rule. And you remember chain rule looks like this here. Right, so if you want to differentiate a composite function, f after g, you start by differentiating the outer function, evaluating that at the argument, at g of x, and then you multiply by the derivative of the argument. You know how it looks complicated, but you know how to do that in practice. And also this integration by substitution rule, it looks complicated if you try to write it down properly, but it's actually not that hard to apply that in practice. So again, we'll take a look at some examples in just a minute. Right, so if you want to move that into the integration word, well, if f is an antiderivative, capital F is an antiderivative of f here, then you can express that in this way. So the derivative of capital F of g of x using chain rule is this, and capital F prime is just f because capital F is the antiderivative of f. So this is what it looks like. Right? And in other words, that means you can integrate an expression that looks like this, and the integral is that. So basically, you just have to integrate this outer function, this f function here, if your argument or integrand looks like that. The hard thing about this is, of course, to identify the correct functions f and g, and to notice there is something like a g prime at the end of this expression. That might not always be easy. So that's why it's a little hard to write that formula down correctly. Here's the formal notation, but I guess we don't want to dwell too much on that. Let's rather have a look at this formal procedure. So there's a formal procedure that makes it easy to apply that rule, and we rather talk about that now. So let's say we want to determine an integral over some function of x, and we want to use some substitution. So let's say this has complicated arguments in x, so maybe it's a sine of x squared something, and you don't know how to handle that x squared. Then one way to handle that is using a substitution. You just kind of define away the complex part. Right? So if this is x squared, you just write y in place of x squared, and then you have a sine of y, and it looks a lot easier that way. Unfortunately, you can't just do that, because by this chain rule, remember, you need to somehow take care of that g prime expression here. That happens if you apply chain rule. So how do you do that? Well, formally, just write down your substitution first, any substitution you want. And then what you do is you differentiate this substitution function. So for example, if your substitution is something like, well, another color maybe, if your substitution is something like y equals x squared, then you would then compute dy by dx. So you differentiate this y as a function of x, and x squared differentiated is just 2x. Right, so that's going to be the g prime of our expression that we need. And then what we do is we take this as a formal expression and we solve it for this denominator dx. Right, so we're saying, well, dx is then in this case dy over 2x. So basically what that says is if we want to replace x squared by y in our integrand, then we have to replace dx by this expression in the integrand. And of course, what happens is it introduces y variables, and we'll integrate over those, and it also introduces this x term here. Now, of course, we can't have two variables in the same integral, right? So either we'll have to use this rule here and then replace our x by some y expression, by solving this expression here. Or, hopefully, that vanishes somehow. And if our expression actually looked like something like this, right, then the term that we just computed, basically that is g prime. If that expression has contained that g prime somewhere, then this will just cancel out. Right? This is basically the g prime. This will cancel out with the g prime that has been there all along. And then I'm left with an expression that only contains y's. And hopefully that now looks easier than before, and I will be able to integrate it. Right? So that's the formalism. So write down your substitution, differentiate that substitution with respect to x, solve for dx, and then just replace the dx in the integral by whatever you get here. Make sure your new integral contains only one variable, and then go on with the integration. All right? So again, not formalism here. Let's look at an example. So this is an example of just the formula I've talked about before. Here you have a sine of x squared, right? Integrating a sine would be easy, but integrating a sine of x squared, that looks hard. So what we do is we introduce this substitution. We just say, well, let's replace x squared by y. Then we have a sine of y, and that's easy to integrate. If we apply that formalism, just as I just did here, dy by dx, we get 2x. So we differentiate that expression by x, we get 2x. And then we solve for dx, and we get dx is dy over 2x. And now we take that integral here. We replace our dx by dy over 2x, right? The expression that we just got here. So that's coming from here. And also we replace x squared by y, because that's the substitution that we started with. So now we're here, and as you can see, this integral now contains y's and x's. So we somehow need to do away with the x's. But luckily that solves itself, because these two x expressions just cancel each other out. Right? So I can just reduce that fraction by x, and all that is left is 1 over 2 here. Right? So this is the 1 over 2, and now I have an integral I can solve. Integral of sine y is the negative cosine of y, so I'll solve that. And then at the end, I just undo the substitution that I started with. So remember, y is the same as x squared, so instead of y, I just write x squared. And then I'm done. Now, maybe as a quick remark, if I have a definite integral, so if I have upper and lower bounds a and b, maybe no, not here. I want to start here. So here's my a and b. Then instead of undoing this here in the end, if I do the substitution, formally I'd also have to do the substitution for those bounds here. Right, so those are in x terms, and that means if I change the integral into y terms, I also need to change the bounds into y terms. So those are transferred by just using the substitution. And the substitution says, well, y is x squared. So I get my new bounds from my old bounds by just using that formula. Right, so here I get a squared, here I get b squared. And of course, if you do that, you won't have to do that extra step at the end. You can use the bounds in y terms and use them there. Or as an alternative, you do the computation without bounds first. You do that, undoing the substitution step, and then once you have your antiderivative, you use that to solve this by just using those bounds with the antiderivative. Should yield the same thing if you're doing it right. All right, one more quick example. Integral over x e to the minus x squared. Again, it's easy to integrate something like e to the x or e to the minus x. But with the x squared in there, it's not so easy. So let's try substitution to get rid of that. We substitute y for minus x squared. Almost the same thing. Dy by dx is then minus 2x. Solving for dx yields this expression. So if we use the substitution for solving that integral, what we get is e to the y by our substitution times dy over minus 2x. And again, the x's here, those cancel out. You're left with this integral, and that's easy to solve. And again, in the end, once you solve that, you just undo the substitution step. All right, any questions about that? Maybe let's see a couple more examples for that. One more example is given here in homework 14.2. Let's take a look at part A. Use a suitable substitution, sorry about the typo, to compute the integral of x squared times sine x to the power of 3 plus 2. Question? That's exactly the problem. Yeah, so if the x wouldn't get cancelled there, then formally we're integrating with respect to y, right? So formally the x is a constant. But actually it's not, because it depends on y. It's a function of y. So it is not a constant really. So we just can't have that. Yeah? if you have that situation, you first need to replace the x's by the suitable y expression. So in other words, if I'm still left with an x somehow, for example, here in that example here, right, this was my substitution. So if I'm still left with an x after the substitution step, I would need to solve this here and say, well, if y is x squared, then x is, well, maybe the root of y, depending on the sign of y. Hopefully that works. Or also minus the sign, minus the root might also be correct. We don't know. Hopefully we know something about x by that point. For example, if we have an integration domain from 0 to 5, we know that x is always positive. And then we know which of those is the right solution. And then we'd have to use that and replace x by this square root of y expression here. Right, so we'd use that. Where is it? Sorry. Here in the integral, replace that x if it didn't cancel out, which thankfully it does. And of course, that doesn't look a whole lot easier than before. In fact, it looks more complicated. Yeah, so then probably substitution was either not a very good idea, or you maybe didn't use the right substitution. Even if you know that substitution is the right approach, it might be hard to guess the correct substitution formula. In many cases, it should be pretty obvious, like for example with the homework, but in some cases it might not be obvious at all, and it might still work. Yeah, but again, you can't have two variables that are dependent on each other in the integral before you solve it. So maybe let's remove that annotation here before it confuses people reviewing that later. And instead, let's take a look at the homework again, 14.2 part A, substitution. So the integral we have here is the integral of x squared sine of x to the third plus 2 dx. It already says use substitution, so let's look for a suitable substitution. And what you can hopefully see is this argument of the sign, that's an x to the third. And here we have x squared outside. That's almost the derivative of this expression, right? So this is the g prime in the formula, so to say. So that looks like substitution might be a good idea, and it looks like we want to substitute this expression, right? So this should be our y here. So let's write that down first and say we use the substitution. Y equals x to the power of 3 plus 2. Let's differentiate that expression with respect to x. What we get is 3x squared. And that means dx is equal to dy over 3x squared. Right? And hopefully at that point you can see that x squared will cancel out. Okay, so what we get for the integral is integral x squared times sine y times dy over 3x squared. And that means the x squared cancels out. We have this 1/3. I just move that in front of the integral. And then we're left with, integral over sine y dy. And that's easy to solve. That's just 1/3, and the integral of the sine is the negative cosine, so negative cosine of y plus constant. And finally, let's undo the substitution, so that means we get minus 1/3 cosine of y was, what was it? X to the third plus 2. plus constant. Okay, so that will be the solution for homework 14.2 part A. Good. Any questions about that? Take a quick look at the tweet pack. (14b), let me just take a quick look at 14b. There's a question about that. Would it have been sufficient to stop 2 steps ahead? I don't quite know where you wanted to stop, actually. So maybe here or here. So generally, the question in what was that 14b? Yeah, the question in 14b is, of course, to solve that integral. So you somehow need to get to some expression that looks like this. That has the integral on one side and the solution on the other side. So I don't really see how you could stop earlier. But if you want to elaborate on that one, I'll be happy to answer later. Good question about the warm-up. Quick look back at the warm-up. So if you remember what we did here is, so this function was defined piecewise for the intervals. And the question is it important, basically the question is it important whether the boundaries that we want, so 8 o'clock for example, are contained in the interval or not. Right, so in this case, the question was to integrate from 8 to 17. 8 is not contained here, but it is contained here. Is it important? Is that important? Would it be different if it was like this? And the answer is it doesn't make a difference, right? Changing a single point for the integral doesn't make a difference. You can change finitely many points, the integral will not change. It will only change if you change infinitely many points. So an interval, for example, of course, that will make a difference. But whether you include or exclude the boundary, no difference at all. All right. And I guess that covers those that I can answer right now. Maybe let's just briefly complete that session by going over this last chapter here before we do more examples. Improper integrals, basically that's a pretty simple extension of what we learned. The point here is that possibly one of the endpoints, of the domain of integration, so A or B, might be points where the function is not defined, or they might be infinity or minus infinity. Yeah, so think of something like 1 over x, and you want to integrate from 0 to somewhere, and 1 over x is just not defined at 0. Or think of something like you want to integrate e to the x from e to the minus x, let's say, from 0 to infinity, right? Because you want to know whether this is a finite area or not, and what value it might have. Then, of course, you can do that by taking appropriate limits. Basically, that's all that this chapter here says. So if f is somehow problematic at, for example, this upper bound here, could also be the lower bound, then what you do is basically you replace this expression by, instead of using that actual upper bound, you just use the limit. Yeah? You replace that by a limit that approaches that upper bound from below. For the lower bound, you'd approach it from above. And that is called an improper integral. And if that limit exists, the value of the limit is the value of the integral. Should be pretty obvious, I hope. So basically what you do is you try to compute that integral, and then you try to take the limit, and if it exists, you're good, and if it doesn't exist, well, the integral doesn't exist. And of course, the same thing works here, taken for the lower limit. In this case, of course, you need to take the limit from above. And the same thing works if one of those goes to infinity. And the same thing works if that critical point is somewhere in the middle. So again, take maybe the function 1 over x. You want to integrate that from -1 to +1, right? None of these bounds is problematic, but the 0 in the middle is problematic. 1 over x is not defined there. In that case, you just split it up. Yeah, so that the bound, this t star here, the critical bound is explicit as an upper bound and as a lower bound in that case if you need to split it up in the middle. And again, if both of those exist, then this improper integral here has a value, and that's exactly that. Okay, so generally, if there is any problematic point anywhere in your integration domain, just split it up there and then take the individual limits, and if it all works out, you're good. Question? So if you take an integral from -infinity to infinity, basically the same situation. Now both bounds are critical in a way, and again you just split it up. You say, well, I'm taking my integral from -infinity to, I don't know, -42, and then from -42 to +infinity, and of course that -42 is completely arbitrary. Take whatever is best suited. Usually 0 is a good choice. Okay, so basically that's all there is to know about that. Quick example. So here's that function e to the -2x. I want to integrate that from 0 to +infinity. So I want to know whether that surface area here is bounded. And I do that by just replacing that infinity by a t and then taking the limit as t goes to +infinity. I compute that integral as usual, right? I get that. I substitute those bounds, I get this expression, and then I just try to compute the limit. And in this case, it's straightforward to do that. And the answer is 1 over 2. Yeah, so it's the same as usual integration, but just take the limit at the end. Only thing you need to watch out for is splitting up the integral if necessary. Here's another example, integrating over 1 over x squared from 1 to infinity. Again, just evaluate the integral, replace this upper bound by a limit, and then in the end, try to compute that limit. In this case, that works, and here you get +1. All right, so if you get your integrals right, and if you can handle limits, this shouldn't be a new challenge, hopefully. Any questions about that? Then I think we still have a little more time for a couple examples. Let's see. What do we do next? Maybe another integration by parts or by substitution. Let's start with 2022 maybe. Jen, where do I have that? Yeah, that one seems nice. Okay, here's another exam problem. So that's 2022, problem number 10. Problem statement says, determine the following indefinite integral. I'm not writing down the text, but here's the integral. Integral over cosine x e to the -2x dx. And just as a remark, if you try to compute such an integral, please always make it clear to the corrector which techniques you are using. So please specifically state you're using substitution. And here is the substitution I'm using, right? I'm using y equals cosine of 2x squared or something like that. If you're using integration by parts, please always make clear what your product looks like. What is f prime, what is g? It makes it a whole lot easier for the corrector to figure out what you were trying to do, especially in case you did it wrong. And that, of course, makes it easier to give points on the approach. If we can at least see you try to do the right thing, but maybe messed it up somewhere, maybe there's still a point for trying to do the right thing. However, if we can't figure out what you were trying to do, there is no point for that. Okay, so let's take a few minutes. That was worth 7 credits, by the way, right? So about 7 minutes. quick question, who of you is done already? And who wants more time? So let's give it a few more minutes. For those who are already done, again, I'm interested in your assessment of how challenging that problem was. There's a tweetback question about that. All right, so let's take one more minute before we look at the answer. All right, so here's your assessment, and as you can probably see, most of you found this rather challenging. So let's take a quick look at that. In this case, you can see there's two types of functions in here. There's the trigonometric function cosine, and there's the exponential function. Both of these are on their own easy to differentiate and easy to integrate. And both have the property that each of these operations basically reproduces a function of the same type, right? So integrating this or differentiating this will get you pretty much the same exponential function up to some constant. For the cosine, integrating or differentiating that will give you the sine, and then doing the same thing again, you'll get back to the cosine. So this might be a case of this rising from the ashes integration method. We do integration by parts, and at some time the integral that we started with magically pops up again, and then we can just solve for that. So that's what I would try first here. I think it doesn't really matter what you differentiate and what you integrate, just as a matter of preference. Maybe let's differentiate that one. So let's call this G, and let's call this G, and let's call this F prime. Right, so this is our F prime, this is our G, and we'll try integration by parts. And be sure to mention that somewhere. Okay, then what happens is, well, let's see. We need to differentiate G, so differentiating the cosine. No, well, first we need to integrate F prime. First we need to have cosine of x, that stays unchanged, times the integral of this, e to the power of minus 2x. If we integrate that, basically we get back the same function, e to the power of minus 2x. And what about the constant? Well, if I differentiate that expression, I get e to the power of minus 2x times minus 2. So in order to cancel out that minus 2 in the integration, that means I need to divide by minus 2. Right? So that's the integral of f. And then I subtract, and now I'm taking g prime here, so the derivative of the cosine is the negative sign, so I have minus sine x here, times the integral of f prime, and I just computed that, that's 1 over minus 2 e to the power of minus 2x dx. Right, so maybe let's simplify that just a little before we go on. This is, I'll write that in front of the expression, minus 1 over 2 cosine x e to the power of minus 2x minus, well, not much to do here. I can take out the 1 over 2. And those two minus signs here just cancel out. Right, so I have sine x e to the power of minus 2x dx. And now looking at that, you see this here reproduces nicely. This doesn't, but we didn't expect that. Right? So instead of a cosine, we now have a sine. So at that point, I could think of two possibilities. Either try to replace that expression here using some trick theorem to get back to the cosine. Seems hard here. Or just do it once again. And then that sine will turn into a cosine, and hopefully everything else turns out fine. So I'd give that a try. So once again, let's say this is our G. This is our F prime. Then what we get is, let's just copy that first part here. Minus 1 over 2. First we need G times F. First part is easy. This is G, this is sine x. We already did the integral of that. Remember, this was the expression. So we have minus 1 over 2 e to the power of minus 2x. So reformulate a little. Okay, and then we have minus this integral once again. The derivative of sine x is the cosine of x. So here's our cosine. And again, we computed that integral here already. Basically, that's that same function, e to the power of minus 2x dx over minus 2. So I'll take out that over minus 2, turn that into a 1/2, and minus times minus, that will turn into a plus. All right. So that looks better. This integral here is the very same as this. And we just need to make sure that we can actually solve for that and keep it. So how do we do that? Well, let's see. We have this integral here. And here we have minus 1 over 2 times 1 over 2, the integral. So altogether, that's a minus 1/4. Maybe let's write that down once again before I actually solve. So let's copy that first part here. Then this is 1/4 sine x e to the power of minus 2x minus 1/4 times the integral. And then I can solve. So on the left I have the integral. On the right I have this expression. I take that to the left by adding it on both sides. So on the left that means I get 5/4 times the integral. And on the right I have, well, minus 1 over 2 cosine of x e to the power of minus 2x plus 1 over 4 sine of x e to the power of minus 2x. Okay, and then I just need to solve that by multiplying with 4 over 5 to get my desired integral. Okay, so in the end, this is, let's see, if I multiply this by 4 over 5, what I get is 2 minus 2 over 5, right? Cosine x e to the power of minus 2x. And then plus 1 over 5 sine x of e to the minus 2x. And if I want that to look a little nicer, optionally, I could do something like factor out 1 over 5 e to the minus 2x. And then I have, let's take the sine x first, and then minus 2 cosine x. But that last step is not necessary. All right, so that would solve this integral question here. Yes? That depends on the question. In that case, good observation. You actually have to do that. I don't remember if I took away a point if you didn't. I'd say the more challenging the actual computation is, the less important those things are. If the integral itself is really easy, then of course that would definitely cost you a point if you forgot about the plus c. How to find what? I didn't try, to be honest. So if you instead of setting it this way, if you would try g prime and f, that's what you mean. It will? Actually, don't see how that would get a lot more complicated. I don't think it will. Have you tried that? All right, so I'll just believe you. Pretty much I'd expect the same things to happen, right? I mean, you integrate the cosine instead of differentiating it, still yields a sine expression, so pretty much the same thing. You differentiate that instead of integrating, still yields pretty much the same expression. So I wouldn't expect it to get much more complex, actually. I would be surprised. Maybe you can show me that approach later. Yeah, so I'd say that should work out pretty much the same. Doesn't matter much. But of course, there are cases where it does really matter which one you choose. There are cases where it just doesn't work one way, it does work fine the other, and there are cases where it's easy one way and not so easy the other way. Yeah, basically, that's just a matter of experience, I guess. There's no easy recipe for recognizing that. Yeah, with integrals, things are usually not easy in general. Yeah, I mean, differentiating is easy. There's a couple of rules you just need to follow. For integrals, you need to get the approach right, and even then, it might still be hard. So integrals is the art of high mathematics. All right, any more questions? Otherwise, I'd say it doesn't make a lot of sense to start a new problem today. So we'll do some more examples on Thursday. Have a nice evening, and I'll see you on Thursday.